Dear colleges, good morning. We should start the fourth lectures on formal languages, automata and codes, and our lectures will be devoted to automata. Let A be an alphabet. An automaton, our alphabet A capital, is composed of the set Q, the set of states, a subset I capital of Q, the set of initial states, and a subset T capital of Q, the terminal or final states, and the set E, which is a subset of such product Q, R, and Q, which is called the set of H. The automaton or algebraic automaton will be denoted by the following: a calligraph, or a italic capital is equal Q, I, T capitals. So the automaton A capital is called finite when the set of states Q is finite. A pass in automaton A is a sequence C which consists of F1, F2, and so on, Fn of consecutive edges. Fi, yeah, which is consists of order triple Qi, Ai, and Qi plus 1, where I from 1 to n. The integer n in this case is called the length of the path C. The word W, I1, A2, so on, AN is the label of the path C. What we have? So what is the path? What is the automaton? So we have the Q states. We have initial state, start state, which where we have entrance to them, and here we have a terminal of final states. Yeah, this state, and when we have some arrow, yeah, this arrow we denote by the alphabet A capital. So for example, A, B, C, yeah, and when we have the path from initial states 1 and 2 to 3, yeah, and we have the path BC, yeah. So this path consists of the states 1, 2, and 3, yeah, and we can write the sequence F1. What is F1? F1 is equal 1 B2, yeah, in our case, and F2 2 C3, yeah, and the length of this path is 2, yeah, because the word BC is a label of the path, such path, yeah. Good. So the state 1 in this edge is called the region of C, yeah, and state Q n plus 1 is called the end of the path C. Here we have F1, yeah, these edges, yeah, F1, Q1, A1, Q2, yeah. The usual notation is the following. We have this path, yes, C, from Q1 to Q1 plus 1 with the word W. By convention, there is for each state Q from Q capital a path of the length 0 from Q to Q, yeah. Its label is empty word. So if we have if we have some state Q, yeah, if we have no such arrow, yeah, so if we have no this guy, we have Q, yeah, and then we have this the path from Q to Q has a length 0, yeah, and the label of this path is the empty word. Next, a path C from I to T is successful if I belongs to initial states and T belongs to final states. The subset X of preliminary A capital star recognizes that by automaton A Q R T will be denoted by L of A is defined as the set of labels of successful passes. So example. So we have initial states here. We will denote by I, yeah, and we have final states. It's denoted by T, and this path will be called successful, yeah, if the start of this path will be initial states and the end of this path is the terminal states, yeah. So if we have from initial stage to the final stage any path is denoted by the word by the family of the word W, then and this word belongs to S, there exists so this path here, and other path maybe here loops here, yeah, we have W1 and so on. So this we have that W belongs to X, yeah, and if every word of this set is a set of label of successful passes, yeah, then we shall call X is recognized by automaton A capital. Good. State Q from Q capital is accessible if there exists a path C from I to Q with I from initial states. what is accessible? So the state is accessible. Yeah, we have some state Q. Yeah, if there exists initial state so that there exists a path from these initial states Q1, so on, Qn, yeah, so that there is path from initial state I to state Q, and the state Q is called co-accessible if there exists a path from Q to the final or terminal state T. Yeah, so accessible if we can Q is accessible if there exists a path from initial states. Yeah. And co-accessible if there exists a path from Q to T, where T is a terminal case, terminal states. An automaton is called stream if each state is both accessible and co-accessible. Let P the set of accessible and co-accessible states, and we put A0 consists of all states P such that the initial state is I intersection with P, and the final state is T intersects with P. Then it's easy to see that automaton A0 is stream, and the set of recognized words by automaton A coincide the set of words recognized by automaton A0. The automaton A0 in this case is called the stream part of the automaton A capital. An automaton can be viewed as a labeled multigraph equipped with two distinguished subsets of vertices, the initial and terminal status. Yeah, so if we have an automaton, yeah, we have initial status, yeah, for example, we denote I, and terminal status denoted by T, yeah, and we have some edges Q1 is so Qn, yeah, and so on. Here maybe loops, and we can consider this automaton as multigraph. This multigraph consists of the initial, the two types of vertices initials. So maybe initials here, I1, yeah, and maybe other terminal states, T1, yeah. So we have T1 is terminal, and maybe arrow from T to T1 to T. The multigraph having the set of states Q as a set of vertices and E as a set of edges is called ordering graph of the automaton. An automaton is called strongly connected if its ordering graph is strongly connected. What is strongly connected? That for any pair PQ of vertices, there is this path from P to Q, yeah? What is strongly connected. Just a moment. Where is? Oh, good. So for any P and Q, to any states P and Q, there exists a path from P to Q. Yeah. Maybe here are the states from Automata. Yeah. Let A, Q, I, T be an automaton R and alphabet A. For each word from the pre-monoid R A capital, we denote by phi sub A of W the relation of the set of state Q defined by the following condition. P and Q belongs to phi A of W if and only if there exists a path from P to Q with label the word W. So what is mean? If just a moment, if we have P and Q, any state, so if there exists a path from P to Q with the label W, we shall this denote by the following way: if and only if. It follows from the definition that the mapping phi sub A is a morphism from a free monoid R alphabet A capital into the monoid of relation over the set of states of automaton A capital. The submonoid phi sub A of the free monoid R A capital of the monoid of relation R or the set of states Q is called the transition monoid of the automaton A capital. Clearly, an automaton is strongly connected if and only if its transition monoid is transitive. So we get that an automaton is strongly connected if for any states there exists paths with connected first states and second states, yeah, and this implies that the transition monoid is transitive. If it is transitive, we have a path from Q to P, and P have a path from P to M, then we have a path from Q to M, yeah. And automaton A capital Q QIT is called deterministic if the cardinality of initial states is equal to 1, and if we have two edges PAQ and PAR, this implies that Q is equal to R. This means the following. If we have some state P, and if we have an edge which is denoted by the letter A, and we have R, the edge is denoted by letter A, then the end of this edge, if we have Q and R, the automaton is called deterministic if the initial the number of initial state is equal 1, and if some arrow is denoted by same some arrows denoted by same letters, we guess that the end the state which is denoted by this arrow coincide, that Q is equal R. Therefore, for each state P and any letter A from alphabet A capital, there exists at most one state Q in such that there exists an edge from P to Q, which is with the label A. For P as states of automaton and the letter A from alphabet A capital, we define P multiply A is equal Q if we have the PAQ is the edge of automaton and is equal empty set in other case. The special map from the Cartesian product Q by A into Q defined in this way is extended to words by setting P multiply 1 is equal P for all states P, where 1 is empty words, and P multiply WA is equal P multiply W multiply A, yeah, for any word V, our alphabet A capital, and any letters A small from alphabet A capital. It follows easily that the word U and V, our alphabet A capital, we have that P multiply the word UV is equal P multiply U multiply V. This function is called transition function or next state function of the automaton, or in other terminology, this function or this map is called transition map. With this notation, we have that the initial states of automaton contains only one state here, and the set of recognized word of this automaton have the following forms, that are such words from our alphabet A capital, that are that initial state multiplies the word W belongs to terminal state, to any terminal states, yeah. And automaton A capital QIT is called complete if for all state P and letter A from A capital there exists at least one state Q such that there exists edge from P to Q which is labeled by the word A. So this means the following. What is a complete automaton? Just a moment. So we have some automaton, yeah, it's initial states, yeah, it's a terminal states, yeah, and for any state P and for any label A, there exists only one state Q such that this edge is labeled by the word, the single word A. So if we have other edge from P to Q1, then this edge has label B such that B distant from A. There is only one for any P, yeah, which with label A, with any label A from the alphabet. For example, if we have the following automaton Q2, yeah, which is denoted by the word B, this which if this automaton contains such H, yeah, this automaton is not complete. So the following very nice statements shows that for each automaton capital there exists a complete deterministic automaton B, such that the set of recognized set of automaton A coincides with the set of all recognized words of automaton B. Moreover, if the automaton A is finite, then the automaton B can be chosen to be finite. The proof. Put automaton A is QRIT. We define the automaton B in the following way: RUV. We put R is the set of all subset of state Q, yeah. U is consists of initial states of automaton A, yeah, and we put V is such subset of states such that S which has the following property: S intersect T is not an empty set. And we define the transition function of the automaton B for S for initial states S and the word A in the following way: S multiply A is consists of states Q with Q capital, so that there exists an element of the set S, so that there exists edge from S to Q with label A. We say that this automaton B is complete and deterministic. I propose for you to show this statement to prove. There will be exercise 1 from homework. Good. And the next, I propose you to see the set of recognized word of automaton A considered as the corresponding set of automaton B. It is the second exercise. To prove that the following quality holds. Next. In the following figures, we give a non-deterministic automaton recording all words of our alphabet. It consists of 2 words A and B having the suffix AB. Of course, that if we consider any words with the suffix ABA, yeah. So if we have words of the form ABA, yeah, there's a pass from initial case to the terminal case with label ABA by the word ABA. Also, if we write here any word X, where X is any word our alphabet A, we get that this word we will be a label of the some path from initial states 1 to terminal states 4, yeah, because here we can write it anyway the prefix of the word W, so this prefix the proper prefix will be, or not proper prefix will be, from the Формальні over the alphabet A star. Sorry, from the alphabet A. So, the deterministic automaton of the following figure is obtained by construction given in the proof of the previous proposition. Yeah. Here we can any word of the form X A B, where X belongs to a capital star. We can any word such form we can get by the label of this automaton. By the automaton from this picture. Good. Next. So it's happening that both automaton, the first automaton and the second automaton, have some same number of states. Next, let A, Q, I, T be a deterministic automaton. For each state Q, we put LQ consists such word from the Формальні our alphabet A capital, so that Q multiplied W belongs to the terminal states. And two states P and Q we call it inseparable if LP is equal LQ, and separable if LP is not equal LQ. And a deterministic automaton is called reduced if two distinct states are always separable. What does it mean? So what is LQ? That are such words, yes, that Q multiply W belongs to T. And if we have two states P and Q that are separable, that if for these states such sets are distinct, yeah. Let X be a subset of Формальні our alphabet A capital. We define a special automaton A of S capital in the following way. The state of automaton A capital of X are a non-empty set of the form U in the power minus 1 X for any words U from our alphabet A capital. The initial state of the automaton A capital of X is the state X, which consists which has form the empty word in the power minus 1 multiply X, and the final states are those containing the empty words. The transitional function is defined for the state y, which is equal u in the power minus y x, and letter a from alphabet by the following way. Y capital multiply a is equal a in the power minus 1 y capital. We remark that this defines the partial function. We have that the set of recognized word by this automaton coincides with the set X. It is by induction we can show that X multiply W is equal W minus 1 X for any words our alphabet A. I propose you to prove this statement. Exercise 3. And this follow from this. Consequently, we have that the word V belongs to recognize this set of words of alphabet A capital X if and only if the empty words belong to the set X multiply V, and if and only if the empty words belongs to W minus 1 X, and if and only if the words belong to the set X. And I propose for you to prove the following exercise. There was 3, exercise 4, to prove that the automaton A of X is reduced. So this I shall there's no problem to show it. We have that for such set y which is equal u minus 1x, we have that L of y consists of such words our alphabet A, such that y multiply v belongs to the terminal states, and it is equal this state as such word v, such that u v belong to S. Therefore, we have that L of y capital is equal y capital. So later, the automaton A capital of X we shall call the minimal automaton of the subset X of the free monoid our A capital. This terminology is justified by the following proposition. Let A capital is automaton with state Q, initial state one state I, and the terminal state T be a trim deterministic automaton, and let X is equal L of A. Let A of X is a minimal automaton with states P, initial state J, and terminal state S. And this automaton is a minimal automaton of the set X. The function phi from Q PR to P defined by phi of Q is equal LQ is surjective and satisfies the following condition. Phi of I is equal J, phi of T is equal S, and phi of Q multiply A is equal to phi of Q multiply A. Proof. Let Q be any states of this automaton, and let V be the word our alphabet A capital, such that I multiply Q is equal multiply U is equal Q. Then we have that LQ consists of the such words from free monoid I star, such that Q multiply W belongs to terminal states, and the set of terminal states, and this equal U minus 1x. Since our automaton is stream, we get that LQ is not empty set. This shows that LQ belongs to the states of the automaton A capital of X. Therefore, we get that phi is a function from Q to the set of states Q to the of automaton A to the set of P, the set of state of automaton A X. Next, we show that the mapping phi is surjective. Let u minus 1x belong to the set of states P. Then we have that u minus 1 of x is not empty set. Therefore, I multiply u is not empty, and putting q is equal I multiply u, we have that LQ is equal u minus 1x is equal phi of q. Then we get that automaton A capital of X capital is reduced. Consequently, the map is surjective. Therefore, we get that L of Y is equal Y. Finally, for state Q, which is equal I multiply U, we have that phi of Q multiply I is equal LQ multiply I is equal UA is the power minus 1 of X is equal U minus 1 X multiply A is equal LQ multiply A. This completes the proof our proposition. Assume furthermore that automaton A in the proposition is reduced. The function phi from Q to R is bijection which identifies the automaton A with the minimal automaton. In this sense, there exists just one reducing automaton recognizing a given set. Let A with the state Q, initial state, single initial state I, and terminal state T capital be a deterministic automaton. An equivalence relation ρ on the state of on the set of states Q is called a congruence if for all states P and Q from Q capital and for all letters A from alphabet A capital if P is equivalent Q by model of ρ and P multiply A and Q multiply A are defined that P multiply A is equivalent Q multiply A by the up to model of ρ. The quotient automaton of the automaton A capital by congruence ρ, which is denoted the third way, has states the classes of the congruence ρ. Its initial state is that a class of initial state of automaton A capital. Its final states are the classes of final states of automaton A capital. The transition function is defined in the following way. If Q is a state of quotient automaton and A is a letter, then Q multiply A is defined if there exists a state P in the class Q such that PA is defined. And in this case, Q multiply A is the class of the state P multiply A. The definition is sound because ρ is a congruence. For example, the equivalence on the state of the deterministic automaton A defined by P is equivalent Q if P and Q are inseparable is a congruence. If the automaton is stream, then the quotient is a minimal automaton of the set of all recognized words by the automaton A. Let A with the states, the set of states Q, initial states single initial state I, small, and the set of terminal state T capital B, deterministic automaton. We consider the set F of partial function from Q into Q. These functions are written on the right. If Q is states and M is a function, then the image of Q by the map M we shall denote by Qm. Composition is defined by the following formula. Here is composition, yeah. This is image by Q, and hence we get the first we calculate the image of Q by M, then the image of this by N. Therefore, the set F capital admits a monoid structure with such operation. Yeah, let phi be a function to a word W, our alphabet A capital association, the partial function from Q into Q defined by the formula Q phi of W is equal Q multiplied W. The function phi is a morphism from the free monoid A capital star into the monoid F capital. The monoid which is an image under the mapping phi of free monoid A star of monoid F is called transition monoid of the automaton A. This is consistent with the terminology for data automata because partial function are particular case of the binary relation. We remark that if we put X is the set of all words which are recognized by automaton A capital, we have that phi minus 1 phi of X is equal X. Indeed, if W belongs this set phi minus 1 phi of X, if and only if the phi of W belongs phi of X, which is equivalent to the I where I is initial states, phi of W belongs to the set of terminal states, that is W belongs to the set X. A morphism phi from monoid onto monoid M to monoid N is said to recognize a subset X of monoid M if phi minus 1 phi of X is equal X. A subset F of a monoid M is recognizable if it is recognized by morphism onto a finite monoid. Let X be a subset of the free monoid our alphabet A capital. For the word W for our this alphabet, a par U ordered par UV of the word such that UW belongs to S is called a context of the word W in the set X. We denote by gamma of W the set of context of the word W defined by the in the following way: gamma of W consists of such pairs, order of pairs U and V that are words, U and V are words, our alphabet A capital, such that U, W, V belongs X. The syntactic congruence on the set X is an equivalence relation. So similar X on A star, which is defined in the following: W and W prime are equivalent on this relation if and only if gamma of W is equal gamma of W prime. It's easily verifies that such relation is a congruence on the set X, and I propose you to prove this as exercise 6 here, that such a relation is a congruence on the set X. The quotient of the free monoid our alphabet A capital by this relation is by definition the syntactic monoid of the set X. We denote this monoid by M capital of X, and we denote by phi of sub X the canonical morphism from free monoid A capital star onto monoid M capital of X. We remark that this canonical morphism recognizes the set X. Proposition 1.4.4. Let X be a subset of free monoid A capital star, and let phi is a surjective morphism from A capital star to monoid M. If phi recognizes the set X, then there exists a morphism psi from M onto the synthetic monoid M of X, such that the following equality holds: phi sub X is equal a composition of phi, psi, and phi. We shall prove this proposition. We remark that sufficient to show that phi of W is equal phi of W prime implies that phi of phi sub X of W is equal phi sub X of W prime. Indeed, if this condition holds, that for an element M from monoid M capital, we have that the image psi of M is defined as the unique element of phi sub X of phi minus 1 of M. And to show property, this property, we consider the ordered pair U and V from gamma of W. Then we have that UWV belongs to S. Therefore, we get that phi of U, phi of V, W phi of V belongs to phi of X. Since phi of V is equal phi of W prime, we get that phi of U, phi of W prime, phi of V belongs to phi of X. Since mappings phi recognize the set X, this implies that the U W prime V belongs to X, and hence we have that UV belongs to gamma of W prime. This completes the proposition 1.4.4. X proposition. Let X be a subset of the free monoid A capital star. The syntactic monoid of X is isomorphic to the transition monoid of the minimal automaton A capital of X. We shall prove this proposition. Let M be a transition monoid of the automaton A capital of X with the states Q capital, initial states initial states consists of single element A small, and terminal status which is denoted by the T capital, and let phi be canonical morphism from the free monoid A capital star to the monoid M. By formula as 2, the morphism phi recognizes the set X, and by previous proposition there exists a morphism psi from the monoid M onto the syntactic monoid M capital of X, such that phi sub X is equal the composition psi and phi. It's sufficient to show that the morphism psi is an ejective mapping. For this, we consider two element M and M prime from monoid M capital, such that psi of M is equal psi of M prime. Let W and W prime are worth from our alphabet A capital, such that phi of W is equal M and phi of W prime is equal M prime. Then we have that phi sub X of W is equal phi sub X of W prime. To prove that phi of W is equal phi of W prime, we consider the state P and let U be the word of alphabet A, such that P is equal U minus 1x. Then we have that P phi of W is equal P multiply W is equal U V minus 1x, and this consists of the such word V, our free monoid generated by alphabet A capital, such that UV belongs to gamma of W. Since gamma W coincide with the set gamma of W prime, we get the P phi of W is equal P phi of W prime. Therefore, we get that phi of W is equal phi of W prime. That and hence we get that M is equal M prime. This completes the proof of proposition 1, 4, 5. Now we summary some of all properties are specific to finite monoid. The following theorem: let X be a subset of the free monoid A capital star. The following conditions are equivalent. The first condition: the set X is recognized by a finite automaton. The minimal automaton A capital of X capital is finite. The family of sets U minus 1 X capital for the word U from our alphabet A capital is finite. The syntactic monoid M capital of X capital is finite. The set X is recognizable. So at first we show that implication from 1 to 2 holds. Let A be a finite automaton recognizes the set X. By proposition 1 for 1, we can assume that automaton is deterministic. By proposition 1 for 3, the minimal automaton A of X is finite as well, and hence the implication from 1 to 2 holds here. The implication from 2, 3 and from 3 to are clear. And next, the implication from 2 to 4 holds by previous proposition. So what is our previous? Yes, this proposition. And by the fact that the transition monoid of the finite automaton is always finite. Implication of, from statement 4 to statement phi is clear, and we shall prove that statement phi implies statement 1. Let phi be a morphism from the free monoid our alphabet A to any monoid M, where M is a finite monoid, and suppose that the morphism phi recognizes the set X. We put A capital is an automata which is consists of the states M capital. So the initial state is empty words, and the terminal state is the image of the set of the free monoid A capital star, yeah, under the mapping phi. And then we get that such automaton be deterministic. And this automaton has a transition function which is defined by the next formula. M multiply A is equal M phi of A, where A is any element of the alphabet A. Then we have that 1 multiply W belongs phi of X in only if phi of W belongs phi of X, thus if and only if W belongs to X. This shows that the set of recognizers of this the word of this automaton coincides with set X. This completes the proof of our theorem. Very nice theorem which describes all types of recognizing of the recognized set by finite automaton, by any automaton, because the set is X is recognized if and only if this set is recognized by finite automaton. So we finish our lecture. I wish you good luck to solve my exercise, which were proposed in this lecture. Goodbye.